Good morning. So I will continue on this microwave, and I will tell you something about the systematic errors which are influencing microwave links. And I was actually talking about microwave links also 2 years ago and also 6 years ago, which was my first year of PhD. And 6 years ago, we were actually presenting here some numerical experiment with some microwave link data, trying to find out what is the potential for urban rainfall monitoring. And since then, we started to collect our own data in 2013, and so now we have almost 4 years of data, and I think that we are slowly, we and also the other groups are slowly moving to some kind of like technology demonstration phase. We are starting this January kind of industrial project with the Prague municipality, mobile phone operator and water utility to really like test how they could benefit from this new source of data. However, even though we are like in this demonstration phase, there are still like big challenges in terms of accuracy of microwave links, and especially some systematic errors. And the main problem is we can describe very well how the physics behind attenuation of the microwave link by raindrops. We can also like fairly well approximate it with some power law and say how much it will be attenuated along its path, and vice versa, find out how vice versa, like convert this specific attenuation to rainfall intensity. But the problem is that we do not measure the raindrop attenuation, but we measure this difference between transmitted and received signal level. So we have to introduce some baseline, basically like taking attenuation during dry weather. But when it starts to rain, the antennas get wet, and this causes some additional attenuation. And this is pretty huge problem, because this attenuation can be several dBs, and it's not so easy to describe how the water layer will be formed on surface of antennas, how quickly it will be drying, and so on and so on. And we look like this is a nice example from Wageningen University. I think it's Lotte's group about like showing spraying of 2 antennas, just artificially spraying, and you can see that one antenna reacts really like quickly on this spraying and dries to some level very, very quickly, and the other one has much like kind of slower drying dynamics, and of course this can be different in the network, and it's difficult to like find out how to quantify this wet antenna dynamics and quantify how big will be the wet antenna in different within different devices. And actually, proportionally, this wet antenna attenuation is maybe not so big by long links, which are attenuated along long paths, but where you have some short links, like 1 kilometer, they are really both affected by this BS proportional, and these links are potentially most informative for urban rainfall monitoring. So it would be very important to be able to kind of quantify this error and maybe filter it out. And in this analysis, I'm like looking at how to do this without some or with limited additional data. And actually, we tried some adjusting and also quantifying based on climatological data, and that's what I will be talking about. So correcting bias using this like long links, which are less affected, and kind of downscaling it or adjusting these short links by the data from long links. Then doing some joint analysis of short and long microwave links to quantify wet antenna, and also looking at very short links where wet antenna attenuation dominates, and which gives us good opportunity to look in the network at different places how big effect this head antenna has. Like this adjusting we tried in our experimental catchment in Prague, Letňany. It's just on a pretty small subset of data, 3 months of data, 13 rain events, and actually we already tried that it's possible to take aerial rainfall from some remote rain gauges, adjust these rain gauges inside of a catchment, and then like based on some cumulative rainfalls, and it significantly improved the high resolution rainfall estimates in the catchment when compared to aerial rainfall observed in the catchment. And we tried the same using, instead of these remote rain gauges, just one longer link. And actually, when you look at the relative error, we are able to reduce this relative error by those short links in the catchment by adjusting it to this long link. These are like these box plots show results for each of the 13 rain events, and like if we take mean of those short links, it's even better. In terms of Nash-Sutcliffe index, we get better values than the values of a long link when compared to this aerial rainfall. But we actually identified with some recent research quite like big problem in this procedure, and we found out that this unadjusted short microwave links capture much better the correlation patterns than those adjusted. So we basically destroy by this adjusting some correlation structure which is there. It's happening probably always, but it was quite a lot influencing performance during heavy rainfalls, and that's what we are interested in. So basically, we were very good in light and moderate rainfalls, but not so good by heavy rainfalls, where this could be like the most promising potentially. So we were thinking about what to do, and probably much better approach is to try to quantify or better parameterize these error models and do some more advanced merging, taking into account different uncertainties. And for this, you need to quantify especially this wet antenna attenuation. So one approach, what I was talking about, is using these short microwave links. We took 2 years of data from city of Prague. We have their microwave links with lengths from 50 meters to half a kilometer. Those very short ones are really insensitive to attenuation by raindrops. When during the rainfall 20 millimeters per hour, there should be its theoretical path attenuation only 0.2 dBs. By those longest links, it's already 3 dBs, which is in a range where we expect to have a wet antenna. So these longer ones are maybe good for quantifying the wet antenna for moderate rainfalls, light rainfalls. These short ones can help quite a lot even during really heavy rainfalls, because we expect even with rainfall intensity 100 millimeters per hour to have really only 1 dB attenuation caused by raindrops along the link path. And of course, the rain gauges are quite far away. This is 5 kilometers, so we have rain gauges 2 kilometers. Some of them, when we are trying to compare it to our rainfall, are maybe 6 kilometers. That's not really good for comparing rainfall at 5-minute resolution. So when we compare it directly, you can see here there is a rainfall in a log scale. Here there is an observed attenuation. You can see something from this. You can see that the shortest links are, the measured attenuation is much smaller than by the longer links. You can see here this black line is this theoretical attenuation when you take this tabled values of this parallel relation and multiply it by the link length. So this is these are attenuations what we would expect from raindrop attenuation, and this difference is probably due to that antenna. But we can probably say that it's increasing function of rainfall intensity, but there is a lot of scatter caused by spatial variability of rainfall, which we are not able to capture at this spatial resolution. So the idea was like making an assumption that really the total attenuation is increasing function of rainfall intensity, and then we can use actually only like a climatological data, take like the complementary cumulative distribution functions, basically like sort the observed attenuation from the smallest one to the biggest one, and do the same with the rainfall. And this like difference should tell us about some like possible wet antenna attenuation which occur in our data set. So here it's maybe 6 to 9 dBs during really heavy rainfalls. During some lighter rainfalls, it will be about 2 dBs. But of course, the problem is that this works only when the total attenuation is increasing function of rainfall intensity. And if our antenna reacts in this way, that when there is a spray of rainfall, it goes up and quickly down after the intensity is reduced, then this assumption holds. But if we would have like really like small, long drying dynamics, it wouldn't work. So the question is if we can somehow find out from maybe climatological data what is the drying dynamics of the wet antenna, or how the links behave. And actually when you compare the time series, this is just one example from these links, you can see that they look kind of like similar. It seems to be that the links are reflecting like pretty well the temporal pattern of a rainfall. And if you look at the autocorrelation functions, this is like a rain gauge, this closest rain gauge, this is like area rainfall, and these are like autocorrelations of these 4 links. You see that it's pretty like similar, and we hope that if we would have just one rain gauge 50 kilometers far away, but in the same climatological region, we could use this rain gauge to look at these autocorrelation function within a few years, and then look at the autocorrelation functions of different links, and maybe say, okay, these links probably have very like similar patterns, so they probably react also the wet antenna in a like that it's an increasing function on the rainfall intensity, and with some other links we should be more careful and maybe treat it in a different way. And like one other option is like looking at the microwave links which are very like close to each other, and we can assume that they were affected by the same rainfall, and they have like different lengths. So if they were affected by same rainfall, and they have same frequencies, they should have same specific attenuations by raindrops. And the total attenuation will be different because they are attenuated along different path lengths. So the longer links will be attenuated more than the shorter links. And we actually observe this total attenuation, and if we would subtract the raindrop attenuation, we would get this wet antenna attenuation. But we don't know this raindrop attenuation, but we can assume that the wet antenna attenuation is same for all these links, and that's not like really. That's very often that at one side they use similar antennas and so on. So it makes sense. And then from these equations you can actually quantify like differential attenuation, quantify the how big ratio of this total attenuation is wet antenna, and how big ratio is this raindrop attenuation. So that's another way how to quantify, maybe in more like operational mode, the wet antenna attenuation and learn more about it. So just to conclude, like correct estimation of wet antenna attenuation is really critical for, especially for those short links. And we are interested in short links because we want to do rainfall runoff modeling with them. If we adjust them to long links, it kind of works, but we destroy this correlation structure, and it's not good for capturing the strong rainfalls. But there are pretty promising possibilities how to quantify that antenna attenuation even when there is no like direct or close by rain gauge, or with this combined use of long and short microwave links, we actually don't need any rain gauge, and we should be able to, at least to some extent, either correct for this wet antenna or quantify like possible errors caused by this wet antenna effect, and then improve some merging methods and create some reasonable final rainfall product. And I forgot to put here logos, but I should acknowledge the T-Mobile. They are providing us data for free, and we hope they will not stop with that once they will find out that it's not so easy to sell it later. Thank you. And actually, if you would have for me some like hints later on, if this is also used in some radar adjustments and so on, I would be very happy to read some papers about using climatological data to correct some sensors.
Thank you. Questions? On the graph, we choose two antennas with different dynamics of driving. Have you studied one antenna in various events? Because it may be that under different conditions, for example, different wind speed, the dynamics of the driving, even the same antennas.
Yeah, actually, we were trying to. We had some like probes on antennas, but it was at the end pretty difficult to interpret the results, and we would probably need really like a dedicated field campaign with many rain gauges along the link. But this is possible with one link and not with like multiple links. So we decided for some bit like approach where we use data what we have and try to find out or try to learn from operational data.
Thank you. I'm curious, have you seen any other disturbance of the signal apart from microantenna?
Actually, not really in a city. I know that there are like, or actually, there is very often some like erratic behavior of a hardware. That's something you need to like really like important, I think, research topic, and there has not been done much on this. But like things which would be like connected to propagation, I think in our case the network is working pretty like expectable.
Does the exposition of the antenna towards the rain or away from the rain play a role?
Yes, I think it can play a role, but for this you really need to have a rain gauge, or maybe even something else than rain gauge, because like when there will be wind, there will be also like huge errors on your rain gauge. So this is really not trivial to quantify and study. Maybe some like lab experiments would be good for this.
Did you check the capability of the links to detect really dry periods? Because I think if a radar says, oh, in this pixel we have this volume, and like the links say, no, on the ground there's no rainfall, that this could also be valuable.
Actually, some of those links, or most of the year, they were performing pretty well, or it was easy to determine the dry weather and wet weather. What was not easy to filter out snow events with the wet snow which occur there, because they cause enormous attenuation. And also, like during the autumn, there is a lot of dew forming on a surface of antenna. It has different dynamics than rainfall, but it's also not like, it's easy to detect it visually and not so easy to detect it, to automate the procedure to be really like, to really catch it.